Class. Today we're going to be building on some of the stuff that we learned in the last lecture with mass calculations. So hopefully this isn't too much of a jump. You should see that it's pretty much the same thing. We're just going to be applying it in a few different ways here. Okay. Alrighty, here we go. All right, let's go ahead and practice this concept that we learned from last lecture. Okay, so the question says you react 4.6 grams of sodium with oxygen to form sodium oxide. So our first step in this is going to be to write out the chemical equation. So we're reacting sodium, sodium metal. Okay, so it's a solid with oxygen, okay, which is gas. And again, whenever it says oxygen, it's O2. Oxygen is a diatomic molecule, so it's always O2. It's never just by itself. And we're forming sodium oxide. So hopefully we've had some practice doing ionic equations, and you could come up with that formula for sodium oxide. How many grams of sodium oxide do you expect to form? Okay, so first we need to balance this equation. This one's pretty simple. Now we have two sodium ones, or sorry, we actually need to do the 2 on the right side first, right? Because we need 2 oxygens, and that gives us 4 sodiums. So we actually need a 4 here in front of the sodium. Sorry, that's kind of messy. Okay, so now we should be balanced. We got 4 sodiums on the left, 4 sodiums on the right, 2 oxygens on the left, and 2 oxygens on the right. So now if you use kind of that web that we talked about in the last one, the way you'd write this out is you have 4.6 grams of sodium. Okay, and we need to convert grams of sodium to moles of sodium. Okay, so we're going to need the molar mass of sodium, which I believe is like 24. No, it's 23. Okay, back that up. 23.0 grams of sodium for every 1 mole of sodium. Okay, and then we convert from moles of sodium to moles of sodium oxide, because that's what we're converting to. So if we use the coefficients from the chemical equation, we can say 4 moles of sodium gives us 2 moles of sodium oxide. And then we convert from moles of sodium oxide into grams of sodium oxide using the molecular mass. So it'll be 4662 grams of sodium oxide. Okay, and that should give us the product there. Okay, got the mass right. Okay, run through that calculation and you would get your answer, 6.2 grams of sodium oxide. Cool. So when we do these mass calculations, we make a couple of assumptions. One is that the reaction goes all the way to completion, so that all the reactants are converted into products. Okay, so an example of that is, or of that not happening would be like maybe only 90% of the sodium actually forms sodium oxide and 10% doesn't react. Okay, in certain reactions that might be true, but when we're doing the mass calculations, we're assuming that all the like in the last example, all the sodium gets converted into sodium oxide, and we're also assuming that only that product is formed, right? We're saying only sodium oxide is formed. In reality, there are other products, other byproducts that happen. So with the example we just looked over, you know, maybe 80% of the sodium turns into sodium oxide, but then 20% actually turns into sodium hydroxide. If it mixed with some hydrogen or some water that was in the air or something during the reaction, those things can happen. So we're making these assumptions just in order to make the math simpler and to be able to predict kind of what's going on. And again, in reality, many reactions do not go all the way to completion for a few different reasons. and multiple side reactions convert reactants into other molecules. So you get byproducts basically. We're going to talk a little bit about yields, and there's 3 yield terms that you'll need to know. First is theoretical yield. So this is basically your mass calculation, okay? So when you do the mass calculation like we talked about in the first example in this PowerPoint and in a bunch of the examples in the last PowerPoint, okay, this is giving us our theoretical yield. This is in theory, if we make all these assumptions, right, this is how much we would expect to get is kind of what we do, or that's kind of what we're saying when we do the calculation. Actual yield is how much you actually measure. So in the first example, let me back up, right? We said the answer, we would expect to form 6.2 grams, right? This is our theoretical yield. This is how much we expect based on all these assumptions we made. But when we do this reaction and then weigh out the product of sodium oxide, maybe you only got 5 grams or something like that, okay? So how much you actually get is the actual yield. Makes sense? And percent yield is the ratio of the actual yield to the theoretical. So let's say, I think there's an example here. Oh, yeah, I have an example coming up. All right, we'll just use this example. Cookie dough example of percent yield, okay? So let's say you made enough cookie dough for 5 dozen cookies. But then someone comes along and eats some of the dough, right? They sneak behind, they eat some of the dough. And you cook your cookies and you only get 4 dozen, right? Obviously your percent yield is less than 100. So theoretically you should have had enough for 5 dozen cookies, but you actually only got 4 dozen cookies, okay? So theoretical yield is 60 cookies, right? That's 5 dozen. Actual was 48 cookies, which is 4 dozen. So the way to calculate your percent yield is to take how much you actually got divided by what you should have got, the 60 cookies, multiply by 100 and you get your 80%, right? So 48 divided by 60 is 0.8 on your calculator, and then you multiply it by the 100%. So multiply by 100 basically, and you're going to get your percent yield. Okay, so 80%. So you got 80% of what you should have got basically. So here's an example in terms of a chemical reaction. Okay, so we have this chemical reaction here where we have carbon is combining with oxygen to form carbon monoxide. The question is saying, what is the percent yield if 40 grams of carbon monoxide are produced when 30 grams of oxygen react with excess carbon? Okay, so 40 grams of carbon monoxide are produced. Okay, that's telling you that that's actually what happened. Okay, so this is our actual yield. We actually got 40 grams of carbon monoxide. We started with 30 grams of oxygen. So in order to calculate percent yield, which is what the question is asking for, right? We need actual yield and we need theoretical yield. So the actual yield is given to us, right? That's something that will just be given to you in the problem because obviously you can't calculate it or anything. It's just what you observe. So we're given the actual yield, and then we need to calculate the theoretical yield. So again, the theoretical yield is saying, if we had 30 grams of oxygen, how much carbon monoxide could we theoretically produce, okay, if we were in a perfect setting, basically. So the theoretical yield is going to be basically what we've just been doing before with the mass calculations. So we start with 30 grams of oxygen. We convert it to moles of oxygen using the molar mass. We use the mole ratios from the chemical equation to go from moles of oxygen to moles of carbon monoxide. Then convert it from moles of carbon monoxide back to the grams of carbon monoxide, and that tells us we have 52.5 grams, okay? So that's how much we should produce if we start with 30 grams of oxygen. Now the problem's telling us that we actually got 40 grams, right? So we're gonna, for percent yield, we're just gonna divide how much we actually got divided by how much we got, okay? And whenever you're doing this, the top number should be smaller, okay? If you kind of forget which one goes on top, just remember the smaller one goes on top, the actual one goes on top. you can't actually get more than you would theoretically calculate, right? That'd be over 100%. Doesn't make sense. You would notice pretty quick if you flipped them around. Okay, so actual yield is 40 grams. So we take our actual divided by theoretical and multiply by 100, and that gives us the percent yield for that reaction. Okay, so I've introduced just this new topic of percent yield, but again, the main part is this mass calculation that we've done like probably 1,000,000 times by now. Not 1,000,000, but a lot. Okay. Here's a reaction that we usually do as like a demo in class. It's called thermite. I'm assuming you'd probably be able to find it on YouTube if you wanted to. Pretty cool reaction. Converts rust into molten iron, right? So rust is the oxidized form of iron. You've probably heard that. So it's iron oxide. If you combine it with aluminum metal, you actually get a single displacement reaction, right? The oxygen will combine with the aluminum, freeing up the iron. And so you actually get pure iron metal out of this reaction. And then you get rusty aluminum, basically. The oxygen transfers over to the aluminum. Okay. So the question we have here says, if you start with 54 grams of aluminum and produce 54 grams of aluminum oxide, what's the percent yield? Okay, so again, for percent yield, we're going to need the actual divided by the theoretical, okay? Okay, so our actual is this right here. It tells us that we produced 54 grams, so that's our actual. And we're starting with 54 grams of aluminum, so we can calculate what we should theoretically get starting with 54 grams of aluminum, and that's just doing one of those mass calculations, okay? Okay, so we start with 54 grams of aluminum. We're going to use the molar mass to convert from grams of aluminum to moles of aluminum. Convert from moles of aluminum to moles of aluminum oxide, and that's just using the coefficients, right? So 2 moles of aluminum equals 1 mole of aluminum oxide, which we have here. Convert from moles of aluminum oxide back to grams of aluminum oxide, and it's telling us that theoretically we should get 102 grams of aluminum oxide. So this is our theoretical, let's say theoretical yield. Now we have the actual and we have the theoretical, so we could divide the two and get the percent yield, which is what you see here. Okay, 52.9%. All right, cool. Okay, so that's percent yield. It's a small building block off of the mass calculations. So now we're going to talk about another small building block off the mass calculations, and that's limiting reactants. So before, when we've talked about these equations, we've said, you know, for example, this last one we just did, we're saying if we start with 54 grams of aluminum, how much aluminum oxide could we produce, right? What we don't talk about is how much iron oxide we started with, right? We don't really know. So in the assumptions that we make when we do mass calculations, we just say, oh, there's enough of this to do what we need to do. Okay, so you could say basically there's an unlimited supply of iron oxide. There's a finite amount of the aluminum, 54 grams, right? How much could you produce? That's what we're assuming when we did this equation. But in real life, if you're doing a reaction, you may only have like a half a gram of the iron oxide or something. And in that case, it doesn't matter how much aluminum you have, right? You can only produce as much as your iron oxide is going to let you. And that's where the limiting reactant comes into place. It's going to be the same calculations, just kind of a different idea here. So here's a more, I guess, maybe it's a little easier to understand, kind of just what I was talking about. So to produce one bicycle, we need a frame and we need 2 wheels, right? So if we have 10 frames and 20 wheels, that's easy. We can make 10 bikes, right? And we're not going to have any frames or any wheels left over. But if we have 10 frames and 10 wheels, right? If we just looked at the frames, theoretically with 10 frames, we could do 10 bicycles. But if we only have 10 wheels, that only allows us to do 5 bicycles, right? So overall, we can only make 5 bikes, and we're just gonna have 5 frames that are left over. Another example is if we had 10 frames and 40 wheels, right? With 40 wheels, we could maybe make 20 bikes, but we only have 10 frames. So really, we're only gonna be able to make 10 bikes, and we're just gonna have 20 wheels that are left over. And that's what we're gonna be looking at with these limiting reactant problems, okay? So what we're really looking at is what is going to run out first. Whatever runs out first limits us, okay? So for example, here we're limited by the number of wheels, okay? The number of wheels only allows us to make 5 bikes. Here we're limited by the number of frames, which only allows us to make 10 bikes, even though we had enough wheels to make 20 bikes. And that's kind of what we're doing here. Okay, here's a simple example. This is a 1-to-1-to-1 ratio, so it's easy to see. As far as the balanced chemical equation goes. So let's say you start with 5 moles of carbon and 100 moles of oxygen, right? How much carbon dioxide is produced? Well, it's a 1-to-1 ratio, right? So 5 moles of carbon would produce 5 moles of carbon dioxide. And if we had 100 moles of oxygen, we could produce 100 moles of carbon dioxide. But because we only start with 5 moles of carbon, it doesn't really matter how much oxygen we have. We're only going to be able to make 5 moles of carbon dioxide. So hopefully that makes sense. Yeah, so 5 moles of carbon produces 5 moles of carbon dioxide. 100 moles of oxygen produces 100 moles of carbon dioxide. As soon as the 5 moles of carbon dioxide are produced, we're out of carbon, okay? And we have a bunch of oxygen left over, kind of like in the bike example. Okay, so what we say here is that the one that produces the least amount of product, right? 5 moles of carbon produces 5 moles of carbon dioxide. So carbon is going to be our limiting reactant, right? This is the one that limits how much we can make. Oxygen doesn't limit us because there's an excess amount of oxygen here. Okay. All right, let's look at the thermite, or sorry, this isn't thermite. This is, I think this is the first example we did in the lecture. Okay, so we have aluminum combining with oxygen to give us aluminum oxide. Okay, so if we start with 6 moles of aluminum and 5 moles of oxygen, how much aluminum oxide is produced? This one's not as easy to just do in your head, right? Because you got these coefficients 4, 3, 2, 6 moles, 5 moles. It's going to be a little bit more difficult to do. So the way to set this up is to just do 2 mass calculations, okay? So before, a problem might have said, if we start with 6 moles of aluminum, scratch this part out, how much aluminum oxide is produced, right? And we were assuming an excess amount of the other reagent. But here we're starting with 6 moles of aluminum and 5 moles of oxygen. So we're just going to set up 2 mass calculations, one for aluminum and one for oxygen. And that's how you do these problems. So it's the same thing we've been doing. You're kind of just doing it twice in one problem. Okay, so let's start with the 6 moles of aluminum. We don't need to convert from grams to moles because we're already in moles of aluminum. Okay, and if we convert then from moles of aluminum to moles of aluminum oxide, which is what the product is, right? It tells us that 6 moles of aluminum would produce 3 moles of aluminum oxide. Starting with 5 moles of oxygen, we use the mole ratios from the chemical equation, right? 3 moles of oxygen will produce 2 moles of aluminum oxide. If you run that calculation, it tells us that 5 moles of oxygen is going to produce 3.3 moles of aluminum oxide. Again, after you do these 2 calculations, you look at the smaller number, right? We're only going to be able to produce 3 moles of aluminum oxide here because we only have enough aluminum to do that, even though we have excess oxygen here. So aluminum is the limiting reactant, oxygen, this is what we have in excess, okay? All right. Okay, so then to say, let's see, how much oxygen is left over? Sometimes the questions might ask, yeah, how much oxygen is left over? So if we take, we've done problems like this, we know that aluminum is our limiting reagent, So if we start with aluminum and say how much oxygen is required to consume 6 moles of aluminum, it tells us that it uses 4.5 moles of oxygen. Okay, using 6 moles of aluminum uses 4.5 moles of oxygen. And we know we started with 5 moles of oxygen. So we take the 5 that we start with, subtract the 4.5 that's used when all the aluminum reacts, and we're left with 0.5 moles of O2 left over. Okay. All right. Let's see. Okay. So in this one, very similar, but we're actually starting with grams of each one. Okay. So in this case, we're doing a mass calculation, but we have to start with grams. Okay, so if we start with grams of aluminum, here we're going to first convert to moles of aluminum using the molar mass, like we've done before. Then we can use the mole ratio, so we can go from 4 moles of aluminum to 2 moles of aluminum oxide. And then we can convert from moles of aluminum oxide to grams. And we can say that from 6 grams of aluminum, we can produce 11.3 grams of aluminum oxide. Okay. Do the same thing with grams of oxygen. I'm not going to walk through it. We've done this a lot. 5 grams of oxygen would produce 10.6 grams of aluminum oxide. Again, so because this is the smaller number, okay, this becomes our limiting reagent. Okay. 5 grams of oxygen would only allow us to produce 10.6 grams of aluminum. Since 6 grams of aluminum produces 11.3 grams of aluminum oxide, we're going to have some leftover aluminum. So if we want to figure out how much aluminum is left over, we could say how much aluminum is needed to utilize this 5 grams of oxygen. So let's convert grams of oxygen to grams of aluminum, right? You could say from grams of A to grams of B if you're looking at that map that I drew out in the last lecture. So you're going to first have to go to moles of oxygen using the molar mass and convert over to moles of aluminum using the mole ratio. And then you're going to use the molar mass to convert from moles of aluminum to grams of aluminum. And it tells us that we use 5.63 grams of aluminum. We started with 6 grams of aluminum, so that means we have about 0.4 grams of aluminum left from the reaction. Okay, this is the basic principle and idea behind all limiting reagent questions. Okay. All right, go ahead and pause the video and see if you can do this practice problem here. Okay, let's go over it. So the question says you mix 30 grams of ethane and 30 grams of oxygen. They react to form carbon dioxide and water. Okay, which reactant runs out first? Okay, so this is basically saying, it's basically saying which is the limiting reactant, okay? So we have ethane and oxygen together are producing carbon dioxide and water. So you should write out your chemical equation, right? All right, now you got to balance it in order to use the chemical equation. So you go through the process of balancing, which we've talked about before. I think we've even talked about it with this example. And here are the coefficients that you get, right? If you need help balancing the chemical equations, I think go back 2 lectures where we talked about this. All right, so now we have our balanced chemical equation and we can do our mass calculations. So since this is asking which runs out first, if a question asks like which runs out first or what's the limiting reagent or anything like that, you know you're gonna have to do at least 2 mass calculations. So we're gonna do one with ethane and one with oxygen, right? You do it with each of the reactants in the chemical reaction. Okay. So let's go ahead and do that. Start with grams of ethane, convert to moles of ethane. Right, we're going from grams of ethane over to grams of, what are we doing? Oh, water. So the second question asks, how many grams of water are produced? Okay, so we're going to convert from grams of ethane to grams of water. So in this case, we could call the ethane A, and we could call water B if we're looking at that map that I produced in the last lecture. So in order to go from grams of A to grams of B, or from grams of ethane over to grams of water, we're going to have to go first from grams of ethane to moles of ethane using the molar mass, convert from moles of ethane to moles of water using the mole ratio, then convert from moles of water to grams of water using the molar mass of water. And it tells us that 30 grams of ethane would produce 54 grams of water. Okay, we're going to do the same thing with oxygen. Convert that to moles of oxygen, convert moles of oxygen to moles of water, convert moles of water to grams of water using the molar mass. And this tells us that 30 grams of oxygen allows us to make 14 grams of water. Okay, so you can see here that oxygen is the limiting reactant because it produces the least amount. Okay, so the lower number wins in this case, I guess. So we've answered which reactant runs out first, right? That's our oxygen here because it's the limiting reactant. How many grams of water are produced? Well, 14 grams of water will be produced, right? Because that's all that oxygen is going to allow us to produce. Even though ethane, the theoretical yield with ethane would tell us we could produce 54 grams, we don't have enough oxygen to actually do that. Okay, oxygen only allows us to make 14 grams. What is left over and how much? Okay, so since oxygen is a limiting reactant and it runs out first, it's going to be totally consumed, which means the ethane is what is left over, right? So ethane is left over. And how much? So in order to do this step, we're going to figure out how many grams of ethane are required to burn all 30 grams of oxygen. So we'd start with the oxygen, okay? And convert grams of oxygen over to grams of ethane using that same pathway that we've done so many times. Okay, sorry, I'm just going through it fast because we've done so many times at this point. It's telling us do that mass calculation. We find that 30 grams of oxygen actually uses 8 grams of ethane. Okay, we started with 54 grams, or sorry, we started with 30 grams of ethane. We use 8 grams of ethane to burn 30 grams of oxygen. So we actually have 22 grams of ethane left over after this reaction. Okay. All right, sorry if that was a lot of repeating myself. I kind of feel like we're doing the same thing over and over, just kind of in different applications. The hard part that people run into is knowing when is it just a mass calculation, when is it a percent yield calculation, when is it a limiting reactant calculation. And I'd say, you know, it's a percent yield calculation if they give you an actual yield, right? They say like the reaction actually produces this or whatever. You know, it's an actual yield question. You know, it's a limiting reagent question if it's asking which one is used up first or which reactant is left over, or if it gives you a mass or a number of moles for both reactants, then it's going to be a limiting reagent question. Any of those things would indicate that it's a limiting reagent question. And then if it's none of those, it's probably just a mass calculation. Practicing it will help you notice, but also if you're ever stuck, just try doing whatever you think it is. And for example, if you think it's a limiting reagent question and you start doing it like that and then realize you don't have enough information to actually solve it, then it's probably not that kind of question. So anyway, practicing those is going to help you recognize what kind of what you're going to need to be using, I guess. And then trying to understand like the theory behind it, like we use those cookie dough example for percent yield and the bicycle example for limiting reactants. Understanding that kind of concept would help you understand as well what kind of question you're being asked. So go ahead and practice all that. Hopefully it's a lot of similar. Sorry if you're tired of doing those math calculations. I think we're moving on after this. But it's an important idea, and I think it's a cool way to be able to predict what's going to go on in a certain reaction. So, all right, I think that'll do it for this lecture. We'll catch you next time.